Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video, I will be solving the paper 6 exam for October-November 2023 variant 1. So let's get started. Question 1 says, a student determines the weight of a meter rule using a balancing method. Figure 1.1 shows the setup. The student places a meter ruler on the pivot. She places a load P on the meter ruler at the 90.0 centimeter mark. She adjusts the position of the meter ruler on the pivot so that the meter ruler is as near as possible to being balanced. The ruler balances with the pivot at the 75.0 centimeter mark. Calculate the distance A from the 90.0 centimeter mark to the pivot at the 75.0 centimeter mark and record this value in table 1.1. So we have the distance A is from 90 to 75. So subtracting 90 minus 75, we get 15.0 centimeters. Part B says she records in table 1.1 the distance B from the pivot to the 0 centimeter end of the meter ruler. She repeats the procedure, placing the load P at 85, 80, 75, and 70 centimeter marks. She records the values of A and B in table 1.1. Now we are required to plot a graph of A per centimeter on the y-axis, so we label it, against B per centimeter on the x-axis. So we label both axes to get the first mark in the graph. And we are required to store the y-axis at A is equal to 0. So for the y-axis, the maximum number was 15.0 and the minimum number is 0. Then we divide by the number of divisions. Here we have 4, then another 4 on the y-axis, so the total number of divisions is 8. So we get 1.875, and we compare that to a scale of 1 or 2 or 5. So 1 is too small, so we choose a scale of 2s. Then we start from 0 as required in the question, and we go 2, 4, 6, 8, 10, 12, 14, and the final one is 60. As for the x-axis, the values of B ranged from 75 to 62.5, and we also have 8 divisions on the x-axis, so we divide that by 8. That would give an answer of 1.565. Comparing with 1, 2, and 5, also 1 is too small, so we use a scale of 2s, and we can start from 62 on the x-axis. So 62, then 64, 66, 68, 70, 72, 74, 76, and 78. So we can reach 75 easily. Now for plotting the points, the minimum values were at 7.5. So this is the 7.5 would be at this position. And we have 62.5. That would be approximately at this point. The next is at 9.4. So this is 9, this is 9.4. And on the x-axis we have 65.6, so at this point. The next value is at 11.3. So this is 11, 11.2, 11.3 would be here. And on the x-axis we have 68. So it will be at this point approximately. The next one is at 13.1. 13.1 is here. And on the x-axis we have 71. So this is 71.9. So at this point, right here. And the final point is at 15.0. So this is 15. And on the x-axis we have 75. Which is exactly at this point. Now we try to draw a straight line from the first point to the last point. It's not an exact best fit, so we have 3 points below the line. So if we try connecting to this point instead of the first one, like this, now we have 1 point below the line and 1 point above the line. So this is a good best fit. Now part C says, determine the gradient of the graph and show clearly on the graph how you obtained the necessary information. So we need 2 points on the graph. So I'm gonna use the points I connected the line to. So this one, we draw a vertical line from the top point and a horizontal line from the point at the bottom. So here we have 15 on y-axis against 9.4. So we subtract 15 minus 9.4. And for the x-axis, we have the values here, 75, and at this point it is 65.6. So we subtract 75 minus 65.6. That gives me a value of 0.5957, which we can approximate to two significant figures. So rounding up, this would be 0.60. And the y-axis had unit centimeter, x-axis also centimeter, so we have no unit for the gradient. Now part D says the weight W of the meter ruler is numerically equal to 2g, so we multiply the gradient, which was 0.60 by 2. To get W, that would give an answer of 1.2. And the weight has a unit newtons. Part E says suggest one practical reason why it is difficult to obtain accurate readings for A and B. So we can say that it is difficult to find the exact position of balancing since the ruler does not balance horizontally. Now part F says using only the apparatus provided for the experiment, explain briefly how you would determine the position of the center of mass of the meter ruler. We can say that we would balance the ruler horizontally on the pivot without any other loads, and that pivot would be at the position of the center of mass of the ruler. Question 2 says a student investigates the resistance of a resistance wire. Figure 2.1 shows the circuit that he uses. Part A says the student places a sliding contact C at a distance L 20.0 centimeters from B. He measures the potential difference V across the length L of the resistance wire. He measures the current I in the circuit. The meters are shown in figure 2.2 and 2.3. Now part I says write down the current shown on the student's ammeter. So going back to the ammeter on the left. So in the middle we have 0.7 and we have 5 divisions between 0.7 and 0.8. So each division is 0.02. So this would be 0.76, the third division after 0.7. So recording the current as 0.76 ampere. Part double I says record the potential difference V shown on the student's voltmeter in the first row of table 2.1. Going back to the diagram. So we have 5 divisions between 0 and 1. So the one in the middle would be exactly 0.5. So in the voltage column we write 0.5. Part triple I says calculate and record in table 2.1 the resistance R of 20 centimeter of the resistance wire using the equation R is equal to V divided by I. So we divide 0.5 by the current 0.76. We get a value of 0.7. We are also required to record in the first row of table 2.1 the value of R over L, and L was 20 and R was 0.7. So that would give us a value of 0.035 in this column. Then we are required to complete the headings in table 2.1. So the length was in centimeters according to the question. The voltage is in volts. Resistance is in ohms. So dividing resistance by length, we divide ohm by centimeter. Part B says the student repeats the procedure using length 60 and then 100 centimeters. The readings and results are shown in table 2.1. Look carefully at the values of R over L in table 2.1 and write a conclusion about the relationship between R and L. So the values of R divided by L are almost the same or almost constant. So we say that R and L are directly proportional. So if you divide two quantities by each other and each time you get an exact value or similar values, so it does not change, so the ratio between R and L is constant, so they are directly proportional. Then the justification would be that the value of R over L is almost or approximately constant. it does not change. Of course, in the question or the experiment, it would change slightly due to the errors of the experiment, but we consider them to be the same. Now part C says use the values in table 2.1 to estimate the resistance R2 of 2 meters of the resistance wire. Show your working. So 2 meters is 200 centimeters. In the table, 100 centimeters got 3.3 ohms. So we would use cross multiplication to know how much of the resistance we would get. If we have double the length, we would have double the resistance, so 6.6 ohms. Question 3 says a student investigates the magnification of the image produced by a lens. Figure 3.1 shows the setup. We have an illuminated object, a lens in the middle, and a screen at the end of the bench. And part A says on figure 3.1, measure the height h0 of the illuminated object. So we get the ruler and measure from the tip of the triangle to the base. That gives an approximate value of 1.5 centimeters. Then it says that this figure is drawn 1/10 the scale and we need to measure the distance u. So going back, we measure from the tip of the arrow to the other tip. This is approximately 2 centimeters, so we write it as 2.0 centimeters. The actual object distance u is 20.0 centimeter marks, not 2, so the scale is actually 10, as it said in the question. The student places the lens at distance u is equal to 20.0 centimeters from the illuminated object. He moves the screen slowly until a clearly focused image is formed on the screen. He measures the distance v between the center of the lens and the screen. On figure 3.1, this distance is represented to scale by the distance v small. Using figure 3.1, determine the actual distance v capital between the center of the lens and the screen and show your working. So going back to the diagram to measure the distance v, we again measure from the tip of the arrow to the other tip. So we here get 8 centimeters. Now we say that we multiply the 8 centimeters by the scale, which is 10, getting a value of 80.0 centimeters. Part I says calculate and record in table 3.1 the magnification m using the equation m is equal to v divided by u. So we had v 80.0 divided by u, which is 20.0. So the magnification is 4.0. And recording the value here, the value for v is 80.0. Part IV says the student measures the height of the image HI that is formed on the screen. The reading is shown in table 3.1 in this section. Calculate and record in the table 3.1 the ratio HI over H0. So we have 5.9 divided by the first reading we got from the question, which was 1.5 H0. We get an approximate value of 3.9. Now part C says the student repeats the procedure using u equals 30.0 centimeters. The readings and results are shown in table 3.1. Another student suggests that the magnification m is equal to the ratio hi over h0. Part I says state whether the results agree with the suggestion. Justify your statement by reference to the results. We say that yes, it is correct, since 4 is equal approximately to 3.9 and 1.16 is approximately equal to 1.2. So we say that the difference between m and hi over h0 is within limits of experimental accuracy. Part I says suggest how you would continue to use the same apparatus to test the suggestion that the magnification m is equal to the ratio hi over h0. We can say that we need to take more readings with different values of u and v until we have at least 5 readings to compare or plot a graph. Question 4 says a student investigates the time taken for water to evaporate to dryness when heated from above. Figure 4.1 shows the setup. The power of the heater is constant. The following is also available: supply of water at room temperature, a meter ruler, and it says plan an experiment to investigate how one factor affects the time taken for the water to evaporate. So we can say that the distance, since we are supplied with a meter ruler, we can say that the distance between the heater and the water would affect the time taken for the water to evaporate. So the independent variable would be the distance between the heater and the water, and the dependent variable would be the time taken to evaporate. You do not need to write about safety precautions, we only need accuracy precautions. You should state any additional apparatus required, explain briefly how you would do the investigation, state the key variables that you would keep constant, these are the controlled variables, and we need to draw a table or tables without any values or readings entered in the table, and explain how you would use your readings to reach a conclusion. So first we can add to the diagram, drawing the heater as a rectangle and another part at the bottom connected to a power supply, and we label it infrared heater as it said in the question. And we place a meter rule right next to the heater to measure the distance between the heater and the water, and then the dish containing the water below the heater, and we draw the level of the water here, and we mark the distance we need to read. So this is the distance from the heater to the surface of the water, for example, and we give it a symbol. I'm gonna call this distance D, and we can add an I symbol to indicate that we need to look perpendicular to the scale, so we do not have to mention it while writing the experiment. And we can say that we hold the ruler using a clamp connected to a stand drawn as a line and a base rectangular on a bench carrying the whole equipment. And we add labels. Here we have clamp, a stand, a meter rule, and we have the dish and water. Now we need to mention the controlled variables in the experiment while we are writing it. So we can start by saying measure a specific volume of water using a measuring cylinder and pour it gently in the dish, so we have the same volume of water each time. Now we say set up apparatus as shown in the diagram and measure the distance D. If we did not draw the line of sight, we need to say by looking perpendicular to the scale. Then we say switch on the heater and start a stopwatch at the same time. Then we wait until all the water has evaporated and record the time T1. Then for the same distance D, repeat the time measurement T2 to get an average time T average. Now we have finished the experiment. We say that we would need to repeat all steps for different values of D, but using same amount of water and same initial and room temperature as controlled variables. Now we write the table. We measured the distance in centimeters. We measured the initial time. We repeated the time measurement, and then we calculated an average time, all in seconds. So these are the table headings and their units. And then we can say that we need to plot a graph to reach a conclusion of D per centimeter on the x-axis against T average per second on the y-axis to reach a conclusion of the relationship between the distance and the time to evaporate. Now this was the end of the exam. I hope you enjoyed this video and found it useful to you, and I will see you in another video.